All right, let's try another video solution here. Let me point out it's from chapter 18, number 13. And the big thing about this chapter was to recognize that everything that we did for the mirrors in 17, we're repeating here for the lenses in 18. Now, you have to be careful because the words about convex and concave are reversed because the mirror reflects the light and the lens refracts the light. That is, it goes through. It doesn't reflect it. So things are reversed. So when I read this one, and I already drew this picture here, I'll read it out loud to you here. But for number 13, it says, use a ray diagram to locate the image of the arrowhead that is 80 centimeters from a diverging lens. So if you remember, the diverging mirror was the convex mirror. So I'm going to draw a concave lens. And I'm going to put a focal length, and the lens has a focal length on each side. And again, that's kind of like the mirror. Although the mirror only had one focal length, the light came in, hit the mirror, and bounced off. So it went by the focal point coming in and then by the focal point going out. And that's what we have here. We have the light coming by the focal point going to the lens, then being refracted instead of reflected, and then past the focal length. So again, everything that we did for the mirrors also holds for the lenses. You just have to remember that one's reflecting and one's refracting. All right, so if that's 40, if I double that, we're talking about an arrowhead right here. Now, again, if you remember, since we spent a lot more time with the mirrors and the lens, the light beam coming here. Oh, let me grab maybe a different color here. So the light beam coming from the top of the arrowhead, parallel to the optical axis, bends away and bends in such a way as if it were coming from the focal point. And the other one, probably the harder one to draw, is the ray that was heading towards the focal point. Now bends and goes parallel to the optical axis. And so has the appearance of coming from right here where these two rays cross. And so we get a right side up, smaller virtual image. And this is kind of the boring lens, sort of like I said, the convex mirror was the boring mirror, because it always made our object right side up. It always made it smaller, and it always made it virtual. Now, if we draw a set of triangles, and for the interest of time, since I did this in the video lecture, let me not go all the way back to scratch, but a set of, I'll put one set, green, would look like this, and this small green triangle would be interlaid to this bigger triangle. And so that would be the height of the object and the height of the image. This, of course, would then be the focal length. And this right here would be the image distance. And so this right here would be focal length minus image distance. This whole thing is object distance. And another set of triangles, maybe I'll do it in blue here, would be the one that would come all the way down, all the way to this focal point here. And it's going to get it kind of busy looking here, but this one would have a small blue triangle here interlaid in this big one. And if you write out your set of similar triangles here, you get something that looks like this. If we call this the height of the image, you would get the height of the image is to the height of the object, as this distance, the focal length is to this whole distance, which is focal length plus object distance. That's the blue triangles. And the green triangles would give you this. And I guess I pretty much did it. I said I wasn't going to redo these ones. You can just go back to the video lectures. But if you study the green triangles, you could have the height here of the image compared to the object as this distance, which is focal length minus image distance, over this distance, which is the focal length. And so there's our two equations. And so I'm going to use those two equations for this scenario. And probably the best warning I can give you for the exam is to write down on a piece of paper these three different scenarios that you can have, and be prepared then to look at your notes and say, okay, which scenario do I have? Starting with, is it concave or it's convex? Well, maybe starting with, is it a mirror or a lens? And then, is it concave or is it convex? Okay. And then if it is a lens, like in this case, if it's a lens and it's concave like this, diverging, then there's only one option. But the other one, the convex, has two options. So then we have to say, okay, well, is the object further away than the focal length or closer in? Because those were our three options there. All right, but for this problem then, let's see. Let me go back to the question. What do we ask for? It says, use a ray diagram to locate the image. So we want to know where the image is, and so we need to do that. Now, this one looks a little harder because we don't really know what the height of the object is. So we can't completely solve this one for the height of the image. We can only put in these parameters. So we know the focal length is 40. So there's the focal length, 40 in there twice. And we know that the object distance is 80. So that's the given numbers in the problem. Of course, that makes 40 over, what's this, 120, which reduces to 1/3, okay? And so we can't explicitly, like some of the other problems, solve for the height of the image because we don't have the height of the object. But that's okay, because we really just need to know this ratio, 1/3, to put in over here. So that's really then what we call the magnification. This is what is the height of the image compared to the object. So I'm just going to put that in for these two variables. We don't know them individually. So that's the 1/3. And then we can put in the focal length of 40, and leaving us with the only unknown here in the problem, which is the location of the image. And so now we can solve that. So I will go 40 over 3 here. 40 minus the image distance. Move this over to here. Image distance, we get a 40 minus. And let's see, this would go in 13 1/3 times. So what does that leave us with? It looks like 26 2/3, or maybe I'll write it as 26.7 then for the position of the image. All right, so there it is. Now, I think the author might be suggesting that you draw this a little more accurately and you can just measure it, and that's fine, but I find the similar triangles to be a much more accurate and better way of getting where the image is located. And they didn't ask for the magnification, but it is 1/3. Hope that helps.